Hello everyone. My name is Mohammed Shehata Saleh. I am PhD candidate at Harbin Institute of Technology, Harbin, China. I'm happy today to talk about the research article titled Efficient Modeling Procedure of Novel Grating Device Using a Multi-Body System Approach. Our paper proposed a multi-body system procedure for a novel aperture grating device, which considered as a complex rigid flexible system. The multi-body model is constructed based on assumption due to the grating movement. This movement can be usefully utilized in different types of application like laser generation and optical communication. Recently, researches and development have made progress in the area of optimization, modeling, simulation, and design of creating device, including kinematics and dynamics analysis. Server method used for the modeling of grating device based on finite element analysis. Finite element analysis can be considered more suitable for modeling elastic bodies subjected to small deformation behavior, while the grating device show definite rigid body motion. The multi-body system dynamic becomes the most economical Vienna in product design and optimization of complex mechanical system, and it can be used for the systems that show definite rotational as well as small deformation. The multi-body model in this paper is used to estimate acceleration and Lagrange multiplier. The Lagrange multipliers can be used to compute the dynamic reaction forces, which can be used in the design process and the optimization process. The numerical manipulation are developed using MATLAB symbolic tool books with very efficient computational procedure. Kinematics of grating device motion. The grating device can be easily defined as a typical parallel mechanism. This mechanism includes two translation joints and one spherical joint, and can make 5 degrees of freedom, move along the x-axis, move along z-axis, and rotate about 3 axes with theta phi epsilon. The dynamic equation of motion that defines the motion of the rigid body and the flexible body can be derived using augmented formulation in this form, where MRR is the mass matrices of rigid body, MFF is the mass matrices of flexible body, CQ is the Jacobian matrices which can be derived from the constraint equation, the partial derivative of constraint equation by generalized coordinate. QR and QF is the external applied forces acting on a rigid and the flexible body, respectively. QD is the quadratic velocity vector. We solve this equation to obtain the acceleration and the Lagrange multipliers. To derive the equation of motion, the constraint equation, we first define point with the point in the grating mass. It can be defined with respect to local frame and defined with respect to global frame with this equation, where A is the transformation matrices function in generalized coordinate. The system can be analyzed as follow. We have about 14 bodies as joint to each other by different type of joints. As example, the fixed base is joined to a ground with fixed joint. The general coordinate for every body can be defined 3 for translation and 3 for orientation. We have 14 bodies, so we have more 100 generalized coordinate, 84 generalized coordinate. The equation, the constraint equation of rigid or fixed joint between fixed base and the ground can be read as this equation 3, 2, constrain the translation, and 3 to constrain the rotational. Also, the prismatic or translation joint can be defined similar to fixed joint by defining points in the action of translation, and define this point with respect to first body, and define this point with respect to second body, and derive the constraint equation for prismatic joint. Also, the constraint equation of spherical joint can be obtained similarly by defining this point P. It can be defined with respect to body 3 and defined with respect to body 4. And as we mentioned before, we can define the constraint equation for the spherical joint. As we can see, we have 3 constraint equations because the spherical joint can constrain the motion in 3 degree x, y, z, but it can allow the joint to rotate about 3 axes. The floating frame of reference formulation can be used to derive the flexible the constraint equation for flexible the connection between flexible body and grating mass, similar to a rigid body. After we solving the equation of motion, we obtain acceleration. Acceleration vector can be integrated to determine the coordinate and velocity for the system. And the Lagrange multipliers can be used to determine the general reaction forces acting in every body. And this equation we can multiply the Jacobian matrices with Lagrange multipliers. We obtain the translation reaction force and the reaction moment or torque. And these reaction forces used for establishing the design process. Based on the multi-body model formulation in the previous section, the grating system model is created using MATLAB symbolic toolbox in the following steps. At first, we built 3D model of the grating device in SolidWorks CAD software. Then the system is fully analyzed to define bodies and joint type. The equation of motion items are the derived function on generalized coordinate. Solving the equation of motion, obtaining system configuration and reaction forces. From the dynamic result, the design mechanical structure for grating detailing device can be optimized. Numerical simulation. The mathematical model of a small-scale grating device is created. Is constructing using the multi-body approach, using MATLAB symbolic toolbox. The initial parameter can be defined in this table, the masses and the inertia of the system. The external applied force coming due to piezoelectric actuator. It's about 4,700 Newton. And the integrator, the Adams-Basha force integrator method are used in the integrator process because it's very it's suitable for system equations that have rigid and flexible body with a small deformation problem. After we solve the equation of motion and integrate the acceleration, we obtain the system movement. The point P in mass that is in the mass grating mass. The point P movement can be computed from the mathematical model in this table. The displacement of grating mass reach about 3.5 millimeter. The orientation of the maximum orientation of the grating mass can reach 2.5 micro rad. The reaction forces can be computed easily. Can be computed also the reaction force and the reaction torque. Also, the flexible body configuration or displacement can be computed, and also the reaction moment acting on the flexible body can be computed and used to define or the flexible body. As a conclusion, we built a mathematical model of grating the file system using multi-body system approach. The type of computational models is important in all phases of analysis, design, and control of such systems. Based on the simulation work of the multi-body model, the optimal design of the grating device can be established. In our going and future work, the multi-body model will be verified with real system and used for full system identification of the grating device to compute and model the parameter like joint fraction and design optimization of the grating device. We tend to finish the real system. It's very complex. Thank you for your listening.